Hey guys, welcome. Yeah, so using example 0 here and two additional examples, examples 1 and 2, I'm going to teach you everything you need to know about exact differential equations. So, a differential equation is set to be exact if it can be written in the form m times dx plus n times dy equals 0, where m and n are both functions of x and y, and if the partial with respect to y of m is equal to the partial with respect to x of n. If both of these things are true, which is even if your differential equation at first sight doesn't appear to be in this form, if you're able to manipulate it or rewrite it in this form, and you check this partial equation, and that's true, then you've got yourself an exact differential equation. And additionally, the solution to that differential equation can be written implicitly in this form. Yeah? Okay, cool. Now, since this is example 0, as with all example zeros, we're gonna tie all these equations and also see where they came from. All right. Okay. Cool. Now, before we do that, let's remind ourselves how chain rule worked in single variable calculus. So, if we have a function y that is a function of x, so let's say y is equal to f of x, and also suppose that x is in turn a function of the variable t, so x is some g of t, and I ask you for dy dt, what you'd do is you'd say that dy dt is equal to dy dx times dx dt. dy dx times dx dt. And you'd be right. This is how chain rule would work in the single variable calculus case, right? But the way we're going to tie all of the formulas for exact differentials is by taking the derivative of this 5xy equals c equation on both sides. And so in order to do that, we need to know how multivariable differentiation works and how chain rule would work in that context. All right, so to do that, let's say that our function phi was such that x and y are in turn a function of t. So we have phi of x of t, comma, y of t, and then we have also that this is equal to some constant c. Then the way we take the derivative on both sides with respect to t would be to do the following. First, we do the partial with respect to x of phi, so phi sub x, and then times dx dt times dx dt, and then we go this plus the partial with respect to y of phi, so phi sub y, and then times, you guessed it, dy dt, and of course the derivative of the constant on the right side is 0, so this equals 0. So this is how multivariate chain rule would work. But in our solution phi here, phi doesn't involve t. Phi is simply a function of x and y. So phi is a function of two variables. Also, y is in turn a function of x. So y is a function of x, and phi is only a function of x and y. It doesn't involve a t. So if we then use this as a guideline and keep in mind that our phi, the solution to our exact differential equation, is only a function of two variables. I know I'm repeating myself, but intentionally. And those two variables are x and y depends on x. Then this here, the differentiation adopted to our situation would look as follows. We'd start again with the partial with respect to x of phi, so phi sub x, but then we multiply by dx over dx, because this time we're taking the derivative of this equation on both sides with respect to x. So we multiply by dx over dx, but that's silly because that's just 1, so I won't bother. I'll just write phi sub x by itself, and then we go plus, so this here is basically this here, but instead of dx dt we had dx over dx, and then plus we'd have phi sub y, right? And then we'd do this time dy dx, right? Times dy dx, right? And that's again because we're taking the derivative of this equation with respect to x on both sides. Okay, and then of course the right side is equal to 0. Now look here. If we take this equation and multiply on both sides by dx, look at what we're going to get. We're going to get phi sub x times dx plus phi sub y times dy is equal to 0. And this explains where this form came from, right? Because then all we have to do now is claim that if we claim that m of xy, or just simply m, is equal to phi sub x, right? And then we say that n of xy is equal to phi sub y. Then this right here is exactly that, right? And so we're done showing where this came from. All right, now next we need to show why this has got to be true. And that's painfully obvious now that we've claimed m to be phi sub x and n to be phi sub y. Because by what's called mixed partials rule, or Clairaut's theorem, or Young's theorem, too many names, 3 names, we know that if we do m sub y here, which is m sub y of that, right? This is the m, which is m right there, right? Then m sub y would read, since this is m and this is m sub y would read phi sub x and then y. Because m is phi sub x, so m sub y would be the partial with respect to y of phi sub x, but that's phi sub xy, right? And that is the partial with respect to x and then y of phi. And then n sub x is going to be the partial with respect to x of phi sub y, which is the partial with respect to y, right? Phi sub y is, right? Okay, so then we're going to get on the right side phi of, it's going to be yx. I wrote my phi very atypically. I normally start with the oval. So let me stay consistent. But yeah, yx, yeah. But so then it's pretty obvious by, again, the mixed partial rule, or Young's theorem, or Clairaut's theorem, that this has got to hold true. Therefore, this has got to hold true. So that's that. And did I forget to mention anything? No. I said that this is the implicit form of our solution. Sometimes once you get to this implicit form, it's possible to solve for y, that is y of x, and get the explicit form of the solution. Sometimes it's not possible. You'll just have to leave your answer in the implicit form, but that's about the only thing I haven't mentioned. Like I said, we're going to use examples 1 and 2 for practice, and that should be sufficient practice, and that's to come soon. But otherwise, I hope you enjoyed this video and learned a lot. All right, take care. Keep watching.